The simplest field theories are free, meaning that the action is quadratic at most in the fields. As an example, we'll consider n fields of the type phi A, where A can be either 1, 2, 3, and so on, all the way up to n. And we can choose, in this case, the action to be simply s of phi. So this will be a function of, in this case, I'm going to use these parentheses instead of the square brackets, because at the end of the day, we are going to consider these phi's here just constants. They do not depend on x. We define this to be 1/2 m. I will define m in a moment. This will be m that depends on two arguments, phi and phi. And this can also be defined as, so this is the definition 1/2 MAB phi A phi B. So this is how you should interpret it. Therefore M, so here we have to sum over A and over B, but M can be thought of as a map that starts from Rn dot, or multiplied by Rn, and goes to R. So if we consider M, it takes two vectors as an input. So the two vectors are phi and phi, because remember that phi is at the end of the day a vector that contains n fields. And what we get from this function is basically this. So we have MAB phi A phi B with this factor of 1/2. Now the partition function, in this case of a free theory, so we have a free zero-dimensional theory, a zero-dimensional QFT. We write the partition function z with the subscript 0 to denote the fact that we have a free theory. We will have to integrate, and we will have to integrate over Rn. Here we have in general d phi, but in this case, instead of this d, we can simply write d n phi like this, because we only have one field. So it is quite intuitive that we have to replace the measure d phi with d n phi. So we'll have to integrate in this manner e to the minus m phi phi divided by 2 h bar in the denominator here. Now M is a positive definite symmetric matrix. In particular, this MAB here, MAB should be thought of as a symmetric. So this is symmetric and positive definite matrix. So we can diagonalize it. That's basically the point. And in particular, so we can rewrite this integral like this, dn phi. I'm not going to write Rn here, but it's going to be implicit, e to the minus 1/2 MAB phi A phi B divided by h bar here. Now we want to diagonalize the matrix, and in particular we are going to define phi, but let's just write phi vector. So this phi vector is just phi A in components, and this can be defined as another matrix, lambda, which will contain the eigenvectors, and then here we can consider another vector chi, like this. So in particular, if we consider phi transpose phi, this will be chi transpose lambda transpose lambda, and here we have chi, not phi. Here we're going to get the identity, because we can choose orthogonal matrices such that lambda transpose lambda is equal to the identity operator, written like this. So I'm using this tilde under this letter to denote the fact that they are matrices, but it's not really important. So we have this, and by the way, phi transpose phi can also be written as phi A, for example, in using index notation. This is just to remind ourselves of index notation. And if we consider MAB, phi A, phi B, this can be written as phi transpose, then we have M, we have phi. This can be written by using this definition as chi transpose lambda transpose M lambda chi. And now we have diagonalized the matrix because we can set lambda transpose M lambda as simply a diagonal matrix which contains the eigenvalues. We can do so because M is symmetric and positive definite, so its eigenvalues will be positive. And therefore, we have rewritten this as chi transpose d chi. So in general, this can be written as a summation of this kind. We have the first eigenvalue, d11 chi 1 squared plus d22 chi 2 squared plus dot 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 plus dnn chi n squared. So you can see that if we use this expansion of this term in the integral there, we will have products of Gaussian integrals. In particular, we can split. So this integral up here will be equal to, so we have something like this. We have the first integral of the kind d chi 1 e to the minus, we have 1 over 2 h bar here, and then we have d11. So let me put d11 here. And then you have chi 1 squared up here. You have to integrate over r. And you have products of such integrals, so you have the same integral with chi 2 and so on, but they will so they will give a very similar result, but instead of d11 you will have d22 here. So here we can simply put this product, and we can take the product over n, and instead of chi 1 we have chi n, instead of d11 here we have dnn, and instead of chi 1 here we have chi n. We have to integrate over r, but this integral is quite simple, so we can put this dnn here at the denominator of h, so we have h bar over dnn. It's convenient to write it like this. Here I put 1, and now this is just simply the variance of the Gaussian distribution. So basically, the first integral will give you the square root of 2 pi, and then you have sigma outside of the square root. But remember, this is sigma squared, so you can put sigma squared inside the square root, and therefore here you will have h bar over dnn, like this. And you have to take the product over n, so this is equal to this, and therefore you can write this as simply 2 pi h bar. When you take these products, you have n variables, so maybe I should not have put n here because we can, let's say, get confused with this n, so maybe I should have called this index in a different manner, like n prime. It would be better. Just let me call it n prime, and we have to take the products from 1 to lowercase n. This is n prime, n prime. Therefore, here we will have 2 pi h bar to the power n over 2, and we divide by, now we have d11 times d22 dot 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 dnn to the power 1/2 here. But now this is just, this product is simply the determinant of the matrix D. But the determinant of D is equal to the determinant of M because of this quantity here. So the determinant of D is equal to the determinant of lambda transpose m lambda. But now, due to the properties of determinants, this is the determinant of lambda transpose, which is the determinant of just lambda. Then you have the determinant of m, and you get another factor of determinant of lambda from here, but you will have determinant of lambda squared. But now, since we know that lambda transpose lambda is equal to the identity, we also know that the determinant of lambda squared will be equal to the determinant of the identity, which is just 1. So this factor is equal to 1. Therefore, this is just the determinant of m. So the determinant of d is equal to the determinant of m. And we get the final expression 2 pi h bar to the power n over 2 divided by square root of determinant of m. So we can either put the tilde here or not, but what I'm referring to here is the matrix M, which is also, I mean, if we use the index notation, this is MAB, like this, and this will be the partition function Z0. Remember that we put this 0 to remind ourselves that this is just a free theory. In the next video, I want to show you how you can generalize this to a more general partition function that takes into account the fact that we might have the presence of a source J, or in index notation JA, which is also, you can think of this as a current, and this will, I will show you how this partition function changes when we also consider these sources.